Hi, welcome to a video podcast on refraction and refractive index. We'll start off by just looking at the concept of refraction to start with. So we imagine some waves travelling from a material where they have a particular speed and then travelling into a material where they travel slower. And I'm just going to draw in, try and explain what's happening to start with, the wave fronts. So these are the crests looking from above, and when the waves get to this new material they travel more slowly, and so this part of the wave front gets left behind the others, and as a result of that process the waves are bent towards the normal. All angles in refraction and reflection are measured relative to the normal, so this would be either the angle of incidence, some people would call it that, or theta 1. And this angle here is the angle of refraction, or some people might call it theta 2. When we're dealing, and that applies to all waves, it could be sound waves travelling between the two materials, or water waves coming into an area where they travel slower, or light. The rest of the video podcast we're really more interested in light. We know that if a wave, we've observed a ray bending towards the normal, it's gone into a material where the waves travel more slowly. Some of you like to say the material is more dense. We must say it is optically more dense if it's slowed the waves down. But we need a number to define how fast those waves are going. So if we can imagine that outside here we have air or a vacuum, then the speed of light is 3 times 10 to the 8 metres per second. If it goes into a material where it slows down and the speed of light in that particular substance is maybe 2 times 10 to the 8 metres per second, rather than having to remember this number, it's a long awkward number, not a convenient thing to keep saying, we define this term the refractive index. And the refractive index is simply equal to the speed of light in a vacuum divided by the speed of light in that particular substance. So in this case it's 3 times 10 to the 8 over 2 times 10 to the 8 is equal to 1.5. And clearly for air in a vacuum the refractive index is 1. The refractive index for air isn't exactly 1, but it's close enough within 3 significant figures to be treated as 1. We can now start using this as a problem-solving tool. We have a thing called Snells Law. And the way I think of Snells Law, we go from a material refractive index 1 to material refractive index 2. So it's very important that you're following the arrows from material 1 to material 2. N1 sine theta 1 equals N2 sine theta 2. Obviously we can only have one unknown out of the 3 pieces of data, but generally the exam board can play a bit clever with this. They might tell you N2 and they might tell you theta 1, so it looks like you've got 2 unknowns, but this is air or vacuum as I've previously stated. Then we use N equals 1. I'll do total internal reflection as a separate podcast. Thank you.